All right, chemists, welcome back to Ralston Valley AP Chemistry's lecture series. We are going to continue our discussions here into Chapter 14. This is the first lecture of Chapter 14, in which we'll be introducing you to properties of acids and bases. Without any further ado, let's go ahead and get started. All right, we'll be beginning here today with a conversation around the definition of a species which we would consider to be either acidic or basic. One of the difficulties about defining acids and bases is that we have a variety of different means we used to define these different species. Many years ago, when chemists were first examining properties of different species in their laboratory, they noticed that a number of different species shared certain characteristics, and they defined those types of species as either being acids or bases. But the difficulty we had was that as we moved further and further into our investigations in chemistry, we discovered that the species which we had initially defined as acids and bases actually shared characteristics with other species in a broader sense. And as a result, we had to modify our definitions of what defines an acid to be an acid or a base to encompass these more broad categories of chemical species. And as a result of that, we ended up with three distinct definitions of acidic behavior. And we'll take a moment now to define each of these different definitions of acid or base behavior for you. So to begin with, our most narrow definition of acid and base behavior is what we refer to as the Arrhenius definition of acids and bases. Specifically, the Arrhenius definition of acids and bases deals with species which are dissolved within an aqueous solution. Arrhenius acids are species which, upon dissociation in aqueous solution, generate hydrogen ions into the solution, whereas Arrhenius bases, conversely, are species which, upon dissociation, will generate the hydroxide ion OH1 negative. There's a couple of very familiar examples of these species that you use in your day-to-day lives. The most familiar acid probably to most AP chemistry students is the species HCl, otherwise known as hydrochloric acid, which is going to fit our Arrhenius definition of an acid because upon dissolving hydrochloric acid in aqueous solution, the hydrochloric acid molecules will dissociate, that is, separate apart into their component ions of H positive, the hydrogen cation, and the Cl negative chloride anion. And as this dissociation yields hydrogen ions in that solution, that would mean hydrochloric acid, therefore, is defined as an Arrhenius acid. Similarly, the base which you're probably most familiar with from our class is sodium hydroxide. And again, you can see how this species will fit our Arrhenius definition because upon dissolving sodium hydroxide into solution, we recognize that sodium hydroxide is a soluble hydroxide compound, and as such, it will dissociate into oppositely charged sodium ions in the solution and hydroxide ions. Therefore, sodium hydroxide is an Arrhenius base. So, that was our first primary definition of acid and base behavior. Now, the trick here is that acids and bases do not solely exist within aqueous solutions. Chemistry happens in the world around us, whether or not it's dissolved in water, and as such, we needed a broader definition of acid and base behavior in order to describe different reactions we observed in different states of matter. And that's where our first of these broader definitions comes in. This is what we refer to as the Bronsted-Lowry definition of acid-base behavior. For this definition, we are going to define a Bronsted-Lowry acid as being a species which is a proton donor, and a Bronsted-Lowry base as a species which is a proton acceptor. Now, please note here that I am notating a proton as the H-positive ion, and recognize that that H-positive ion literally is a synonym of a proton, because the hydrogen ion exists as a single proton with no electron present. So a proton donor is a Bronsted-Lowry acid, the acceptor is a base. This particular definition of acid-base behavior always will come in pairs. That is, one species of an interaction will act as the donor of the proton. Another species which accepts that proton will therefore be the base. So we always define these as being acid-base pairings. Now, what I'd like you to notice here as an example is that we can write our previous reaction, that was the Arrhenius behavior of hydrochloric acid. We can rewrite this reaction in order to describe the behavior from a Bronsted-Lowry perspective. And in order to do that, I'm going to write a slightly more complicated system here in which the hydrochloric acid dissolves in water. And rather than simply showing this as a dissociation, what I'd like to show here is that the hydrochloric acid is actually donating the H positive ion from the acid to the water molecule. And in doing so, we end up forming two other ions. Those are, first off, the H3O positive ion. We call that the hydronium ion. And additionally, that chloride ion, Cl negative, that we saw in the last example. So I want you to understand now that this reaction as written here is really a synonymous reaction of the first reaction we wrote as a dissociation. That is, in a more complete understanding, we would see that the hydrochloric acid molecules in solution really aren't just dissociating, but instead are donating that proton to the water molecule, implying in this instance then that the hydrochloric acid is acting as the proton donor, and likewise the water molecule in this instance would be acting as the proton acceptor, that is the base. So again, we see an acid-base behavior. HCl acts as the acid, water acts in this case as the base. Another familiar interaction that we would see like this would be the interaction as we dissolve ammonia in water. Upon dissolving ammonia, which is NH3 in water, the ammonia acts as a base, that is an acceptor of a proton from a water molecule. So in this instance, water donates the proton to the ammonia, forming the ammonium ion, NH4 positive, and a hydroxide ion, OH negative. So then in this pairing, ammonia is the proton acceptor, that is the base, and water acts in this instance as the species donating that proton, which means water is the Bronsted-Lowry acid in this reaction. So again, we see Bronsted-Lowry behavior here, an interaction between a pairing, that is a donor and an acceptor of that proton. Now, not surprisingly, our broadest definition of acid-base behavior is what we call the Lewis definition of acids and bases. The Lewis definition, not surprisingly, actually is going to be best approached by looking at Lewis dot structures for these different species to understand the interaction between two species in the reaction. By our definition, a Lewis acid acts as an electron pair acceptor, and a Lewis base acts as an electron pair donor. Please be very, very careful here, folks. Many AP chemistry students mix up this definition because they get very used to dealing with the Bronsted-Lowry definition, in which the acid is the donor of the proton. But note here that if I look at the proton, the H positive ion, as being an acidic species, I can recognize that the H positive ion can certainly not act as an electron pair donor because there are literally no electrons present on that H positive ion. That implies, therefore, that the only behavior that we can see exhibited by a proton that is H positive would be in an acidic sense, that is, an acceptor of an electron pair from another species as it forms a bond. So let's take a look at one of these previous examples again and look at it now from a perspective of a Lewis interaction. Have a look again back to the last reaction, which we wrote between the reaction between water molecules and ammonia as ammonia dissolves into that solution. Let's go ahead and now draw a couple of Lewis dot structures for each of those species. These should be familiar species, which we've drawn many times before. First off, we'll go ahead and show water molecule with our central oxygen atom, and then those two lone pairs of electrons present on the oxygen. And then also, we'll draw our Lewis dot structure for the ammonia molecule, NH3, where we see the three bonds to our hydrogens, as well as that one lone pair of electrons on the ammonia. And again, as we saw in that last reaction, the ammonia acts as the proton acceptor, that is, we're going to go ahead and move the hydrogen ion off of the water molecule onto the ammonia molecule. And in doing so, ammonia is going to form a coordinate covalent bond with that extra lone pair of electrons, where it donates the entirety of the electron pair to form the bond to that hydrogen atom in order to form the ammonium ion. And as we see in this interaction, we have now formed ammonium ions and hydroxide ions, implying for this particular behavior, we observed ammonia, the nitrogen specifically in ammonia, acting as the electron pair donor, whereas therefore ammonia is the Lewis base in this interaction. And similarly, we have seen the water molecule acting as the electron pair acceptor, specifically on that hydrogen ion which was donated. Therefore, this is acting here as our Lewis acid. So that Lewis definition here again encompasses a previous interaction which we had seen as a Bronsted-Lowry behavior if we look at it from a perspective of which species is doing the donating versus the accepting of the electron pair as the bond is formed. Now, as a quick side note here, the AP Chemistry test's most favorite Lewis acid-base interaction that it likes to talk about is one that kind of illustrates why that Lewis definition is such a versatile definition of acid-base behavior. As it turns out, Lewis behavior can encompass interactions between species which contain no hydrogens moving from place to place whatsoever. So by far, the AP Chemistry test's most favorite Lewis acid-base interaction to ask you about is a reaction between that ammonia molecule, NH3, and a different species, which is a familiar one we've seen from back in our Lewis dot structures, which is boron trifluoride, that is BF3. And you can see here, as I draw some Lewis dot structures for each of these species, why this particular reaction is such a logical one to observe in terms of Lewis acid-base behavior. Because again, as we previously saw, the ammonia molecule has that lone pair of electrons hanging out on the nitrogen atom, a great place to see an electron pair donor. And then looking at our boron trifluoride, recall that boron here is going to be forming an incomplete octet due to the very low electronegativity of that boron atom in comparison to the fluorines which it is bonded to. And as such, we have one species, the ammonia, with an extra pair of electrons, and the other species, the boron in the boron trifluoride, which has got an incomplete octet and therefore a fantastic place to see an additional 2 electrons donated to form a bond right there. So as we make the bond between the ammonia molecule and the boron trifluoride, you can see we form this big kind of mess of a molecule that is the resulting product of this synthesis, that is BF3NH3, a chemical species that goes by the name of ammonia boron trifluoride. And in this particular interaction, we see again ammonia acting as the electron pair donor, that is the Lewis base in the reaction. And the boron trifluoride here is acting as the electron pair acceptor, that is the Lewis acid. And importantly to note here, folks, there is no transfer of a hydrogen ion or a proton from one place to another within this reaction, implying, therefore, this particular reaction is a Lewis acid-base interaction, but neither an Arrhenius or Bronsted-Lowry definition fits this particular instance. So the Lewis behavior is, as it turns out, the broadest definition, which encompasses a much wider array of chemical reactions than either the Arrhenius or Bronsted-Lowry definitions will. So let's go ahead and move on to have a look at what we refer to as our list of strong acids and bases. All right, on this slide, we're going to have a look at a list of species that exhibit a particular behavior within an aqueous solution. These are the species which we call the strong acids and the strong bases. Now, strength of acids or bases here has nothing to do with how dangerous any of these species are, but instead has to do with the degree of dissociation experienced by the species when dissolving in aqueous solutions. Specifically, for each of these species, at relatively low concentrations of below 1 molar, a strong acid or a strong base will undergo complete ionization, that is, complete dissociation into the component ions within the solution. Now, it's important to be able to memorize these strong acids and strong bases because, as it turns out, the AP test will make the assumption that you know which ones they are, and how we treat a solution will depend very much upon whether the species is acting in a strong sense, that is completely disassociating, or instead if that species establishes an equilibrium and instead exhibits what we call weak acid or base behavior. So right off the bat here, let's just go ahead and list them for us here. There are 3 binary acids that undergo complete dissociation at low concentrations. Those are the acids HCl, hydrochloric acid, HBr, hydrobromic acid, and HI, that is hydroiodic acid. And in addition to those 3 strong acids that are binary acids, there are also 4 commonly encountered ternary acids that we generally consider to be strong acids as well. Those are sulfuric acid, H2SO4, nitric acid, HNO3, perchloric acid, HClO4, and additionally we have chloric acid, which is HClO3. Now, importantly to note here, folks, we want to put a little star next to one of these species here, that is sulfuric acid, H2SO4. You'll notice here that sulfuric acid is the only diprotic acid on our list of strong acids. And by diprotic, I mean an acid which has 2 acidic hydrogens which can be lost into the solution. Now, as it turns out, it is only the first ionization of sulfuric acid that exists as a strong dissociation. The second dissociation, where we lose that second hydrogen, is a relatively weak dissociation. That is to say, the reverse reaction is actually favored in that instance, which means that only a small fraction of the ions of HSO4 negative in solution will undergo further ionization to form sulfate ions SO4 2 negative. So just the first dissociation of H2SO4 is the one we are interested in here for the strong dissociation. So those are our list of strong acids. Note in particular here that there is one of the binary acids which is not a strong acid that you'll commonly encounter within the AP chemistry questions, and that is the acid HF, or hydrofluoric acid. We'll talk a little bit later about why that is in fact a weak acid, but for the time being, I just want you to recognize here that hydrofluoric acid is the only weak of those commonly encountered binary acids from our list of the halide acid families. So, have a look now over at our strong bases. We've got a list of strong bases for you next here. First off, any alkali metal hydroxide will count as one of the strong bases. Those are, number one, lithium hydroxide, LiOH, sodium hydroxide, NaOH, or potassium hydroxide, KOH. If you found yourself encountering either rubidium hydroxide or cesium hydroxide, those would also be strong bases as well, but we hardly ever see them due to the rarity of those alkali metal species, and as such, we're really just going to focus on those three lithium, sodium, and potassium hydroxides. And then additionally, we have three alkaline earth metal hydroxides we also consider to be generally strong species. Those are calcium hydroxide, CaOH2, strontium hydroxide, SrOH2, and barium hydroxide, BaOH2. So calcium, strontium, and barium. Now, interestingly here, folks, you might remember from last year that that list of hydroxides we just gave you right there also, not surprisingly, happens to be the list of soluble hydroxide species. So again, the alkali metals plus calcium, strontium, and barium hydroxides are the soluble hydroxides, which again would imply those are the ones likely to dissociate into aqueous solution. All right, so there's our strong acids and our strong bases. The easiest approach then is just to memorize the strong ones, because at this point now, literally any acid or base that you recognize which is not among that list would therefore count as one of the weak species. And there are many more commonly encountered weak acids or bases we'll see, and as such, memorizing the strong ones tends to be the efficient way to go from an effort perspective there. So let's go ahead now and finish this up here by writing a couple of ionization equations describing what happens when we place each of these following species into an aqueous solution in example 1 here. So have a look for me first of all here at one we've already talked about, that is hydrochloric acid, HCl. I recognize that hydrochloric acid counts as one of my strong acids, and as such, I can write its dissociation, showing the hydrochloric acid splitting apart to form the component ions of the hydrogen ion H positive or the chloride ion Cl1 negative. And then I also would like you to recall that I can write this as a simple dissociation to form those ions, but I also could write this as what we refer to as a hydrolysis reaction, that is a reaction between this species and water, in which the hydrochloric acid acts as the Bronsted-Lowry acid, that is the proton donor, donating that H positive ion to the water molecule, forming in that instance then a hydronium ion, H3O positive, and the chloride ion, Cl1 negative. Either of these two depictions of this particular reaction are equally valid from the AP test's perspective, so you're welcome to use either one, whichever makes you happier. I do recognize here, folks, then, that they are synonymous reactions, because really that hydronium ion is essentially just that extra water molecule associated with that hydrogen ion in that solution. So a hydronium and a hydrogen ion are really just kind of synonymous species in this instance. So there's our first example. Looks like we're in good shape. Let's now take a look at the species HF, that is hydrofluoric acid. Now recall again that we discussed the idea that hydrofluoric acid is itself not a strong but instead a weak acid, and as such that hydrofluoric acid will again dissociate into its component ions in solution, forming the H positive ion and the fluoride ion F negative. But here's the trick. That fluoride ion, as it turns out, is a much, much smaller ion than the chloride ion we just previously discussed in the last example. And as such, when the fluoride ion approaches the hydrogen in this solution, that fluoride ion is much more strongly attracted to the hydrogen ion due to the stronger force of Coulombic attraction due to the smaller size of that particular ion in solution. And as such, the fluoride ion acts as a much stronger base, that is, a better acceptor of the hydrogen ion in the solution, meaning it has a stronger ability to hold on to the H positive in the solution and therefore does not disassociate to the same degree. And as such, in this particular reaction, the reverse reaction is actually favored, meaning we are going to see this establish an equilibrium, which heavily favors the left side of the reaction, implying this species again would therefore be a weak acid. And again, to denote that, we want to make sure that we have that reversible arrow showing the reverse reaction being favored in this instance. All right, so we've got the two acid species here. Let's now go ahead and take a look at our two bases. Oh, again, before we move on, that hydrofluoric acid could also, again, be written as a hydrolysis reaction as well. In that instance, again, it would be HF plus H2O forms now H3O positive hydronium and F negative. All right, sorry about that. Moving on to sodium hydroxide, NaOH. The sodium hydroxide, upon dissociation into solution, will break apart into the component ions of Na positive sodium ions and the hydroxide ion OH negative. This dissociation will essentially go to completion because, again, sodium hydroxide being an alkali metal compound is completely soluble in solution and as such should dissociate 100%, implying this is the behavior of a strong base. Now, in contrast, I could then write the hydrolysis reaction now for ammonia and H3. The ammonia, when placed into water, cannot directly dissociate to form hydroxide ions. So in order to show the acid-base behavior here in water, we must write this one as a hydrolysis rather than as a simple dissociation. So writing my hydrolysis reaction now, the ammonia NH3 will react to water H2O. The ammonia acting here as a proton acceptor or an electron pair donor, that is, a base in this instance by either the Bronsted-Lowry or Lewis definitions. And the water in this case acts as the proton donor, that is the hydrogen ion donor, meaning therefore that water here is our Bronsted-Lowry acid. And in this instance, we'll then form ammonium ions and hydroxide ions, and as such, we would again see this exhibit weak behavior, as this again is not a reaction involving one of those 6 species we have listed on our strong list. And therefore, we would see the reverse reaction again favored, so we should show this with a 2-directional arrow to indicate this system establishing an equilibrium. All right, now that we've had a look at how to write those hydrolysis or dissociation equations for acids and bases, it's time to further dive into our look at acid behavior, specifically by looking at how to deal with weak acids in solution, or weak bases. Now, keep a note here, folks, that weak acids and bases are weak because they do not undergo complete ionization or dissociation in an aqueous solution. And as such, upon dissolving in solution, because that reverse reaction tends to be favored for a weak acid or base, these systems will end up establishing an equilibrium with their conjugate species in solution. So we've gone ahead for you here and written a hydrolysis reaction showing a generic weak acid HA reacting to water in solution. And then recognizing that that acid is a proton donor, it's going to get rid of the H positive, giving it to the water, forming in that instance then the hydronium ion H3O positive, and then that conjugate base anion, the A1 negative ion. Again, you also could have written this reaction as a dissociation as well. We're going to go ahead and look at this from the perspective, however, of the hydrolysis reaction. So let's go ahead and start here by identifying the species which are acting as acids and bases in this system. If you have a look here, the species HA again was our proton donor. That makes this the acid. Water would be accepting the proton, which implies therefore that is the base. And for the reverse direction reaction, the hydronium reaction, H3O positive, is donating that proton, implying that is the conjugate acid. And then the anion there, A negative, would therefore in this system be acting in the role of the conjugate base. And again, because this reaction is a reversible reaction, this system will establish equilibrium. And as an equilibrium reaction, it is governed by the K expression for this reaction. We're going to give this K a special notation here. We're going to call it a Ka, which is the acid dissociation constant. And we can then write the value of our Ka expression the same way we always have. That is the ratio of products over reactants, which in this case would be that product hydronium ion H3O positive times the concentration of the anion A1 negative divided by the molecular acid's concentration, that is HA. And again, recognize I also could write that as the same expression but expressed as a dissociation equation. That would be the concentration of H positive times A negative divided by HA if you had chosen to write your reaction as a dissociation instead. So, given that this is a weak acid, the value of the K expression is going to be a relatively small value of K because, again, as a weak species, the degree of dissociation is not particularly great. And as such, this system favors the reactant side. So now that we've kind of written our expression here, let's take a moment to make a comparison between the properties of strong and weak species in solution. In the table we've got here, we've got a number of different properties we're going to look at here. Those are the respective Ka values, the position of the ionization equilibrium, the relative concentrations of the equilibrium concentration of the hydrogen ion in solution in comparison to the initial concentration in the molecular acid, and then last, the relative strength of the conjugate bases. So starting off here with a straightforward definition here, if we're looking at the K values for a strong versus a weak acid. Recall the K value tells the ratio of products over reactants. For an acid's dissociation or a hydrolysis reaction, the products are the ions. In the case of our generic acid HA, it was the hydronium ion and the anion A1 negative. And because a strong acid undergoes complete dissociation, the concentration of the molecular acid present in the solution essentially is very, very close to zero, implying, therefore, the Ka value of a strong acid would be some number in the numerator divided by a number approaching zero in the denominator, which implies the Ka value would therefore be very, very large. In comparison, for a weak species, because the molecular acid does not to a large degree dissociate, that implies that the concentrations of hydronium and the A negative ion are going to be very, very small in comparison to the concentration of the initial molecular acid. And as such, we've got a larger denominator and a smaller numerator, implying the value of K for a weak acid is relatively small. So in essence, that Ka value essentially tells you the strength of the acid. The larger the value of K, the stronger the acid in the system. Now, likewise, from our conversations we've had during our equilibrium unit, recognize that the K expression is also really telling us about the position of the equilibrium system. And again, for a strong acid, because that Ka value is very large, that implies the products are favored, and therefore our equilibrium position lies far to the right. And likewise, for a small value of K for a weak acid, that implies, therefore, the equilibrium position would favor the reactants, and the position of the equilibrium, therefore, lies far to the left. Another way of looking at the system here would be to compare the relative concentrations of the hydrogen ion at equilibrium in comparison to the initial concentration of the molecular acid HA. Again, as we discussed when we were talking about strong acids, a strong acid undergoes complete dissociation, and therefore that equilibrium concentration of hydrogen ion at equilibrium is approximately equal to the initial concentration of the acid HA, whereas for a weak acid, the equilibrium concentration of that hydrogen ion is going to be much smaller than the initial concentration of the molecular acid HA initially, again, because the degree of dissociation is very small for this species. And last but not least, and this is kind of the one that I want you to take away as your kind of big idea here, recall for a strong acid that implies that the forward direction is heavily favored, and therefore the reverse reaction is much, much less favorable to occur. Remember that species in our equation, the A-1 conjugate base anion, in the reverse reaction is acting as the proton acceptor, that is, as the base. And if we see for a strong acid that the reverse reaction is not favored, that must imply, therefore, that the conjugate base is not a particularly effective conjugate base in this system. So long story short, for a strong acid, the conjugate base is a relatively weak conjugate base. Or comparatively, if I'm dealing with a weak acid, that would imply that the reverse reaction is favored, and therefore the conjugate base A negative is therefore an effective acceptor of the proton from the H3O positive ion. and therefore we would expect to see there weak acids have relatively stronger conjugate bases. Another way of stating that would be essentially that there's an inverse relationship between the strength of an acid and the relative strength of its conjugate base. That is, the stronger the acid, the weaker the conjugate base, and the weaker the acid, the stronger its conjugate base would be. Having now looked at how to deal with weak acids in solution and some of their properties, let's now go ahead and take a look at a couple example problems for you here that have been touched on in recent years by AP chemistry tests. The first of which here is a question asking us to determine what would be the strongest acid and base that could possibly exist within an aqueous solution, and we want to give some reasoning to justify our answers here. So let's go ahead and start off by talking about some just kind of fictitious possible base that might exist in solution that would be an incredibly strong base. We'll give this base the kind of generic name B. And again, let's go ahead and put this into aqueous solution. So it's going to be interacting with water molecules here. And we recognize that if this incredibly strong base B happened to exist in an aqueous solution, bases are fantastic acceptors of protons, and that implies, therefore, that our fictitious base B could pick up a hydrogen off of one of those water molecules, forming the conjugate acid BH positive and a hydroxide ion. And this essentially is going to point us kind of in the direction of our answer here, because that would really imply, therefore, if the base B was an incredibly strong base, it likely wouldn't exist in meaningful concentration within the aqueous solution because it would immediately accept protons from water, forming hydroxide ions. Now, that hydroxide ion we happen to know itself is a strong base, and long story short, what that really tells me then is any base stronger than hydroxide in solution will effectively pull hydrogens off of water, thus forming hydroxide in solution, implying, therefore, the strongest base that could possibly exist within the solution would therefore be the hydroxide ion itself. And we can apply a similar logic in terms of how to deal with acidic species. If we imagine for a moment an acid that we are familiar with that is a very strong acid, let's take a look at one familiar one like hydrochloric acid. We know that a strong acid, hydrochloric acid, does not meaningfully exist in concentrations we would expect to be able to detect in an aqueous solution because that acid is essentially going to be a fantastic proton donor. And as such, if we place hydrochloric acid into water, it will undergo, in this case, a hydrolysis reaction, donating that proton to the water molecule, forming hydronium ions, H3O positive, and then the conjugate anion, Cl1 negative. So long story short, the hydrochloric acid is too strong an acid to itself exist in molecular form within the solution, and therefore any acid which is a significantly strong acid will then produce hydronium ions in solution, implying therefore that that hydronium ion must therefore itself be the strongest acid that could possibly exist within the aqueous solution. So long story short, the strongest base that can exist in aqueous solution is the hydroxide ion. The strongest acid that can exist within the aqueous solution is the hydronium ion. And any acid or base which is stronger than either of those respective species would just end up undergoing a hydrolysis reaction to generate each of those species within the solution itself. All right, example number 2 taken care of. Let's move on now to example number 3. This is a straightforward problem that you have seen from back in your first year of chemistry class here, where in this instance going to ask you to identify the acid, the base, the conjugate acid, and the conjugate bases in each of these following reactions. So again, remember here we are looking to our Bronsted-Lowry definition, which tells us that the acid is the proton donor and the base is the proton acceptor. In the first reaction, we have water reacting to H2CO3, forming H3O, 1 positive, and HCO3, 1 negative. And let's take a look first at that forward reaction. In the forward direction reaction, the species H2CO3 on the left side of a reaction has 2 hydrogens there. On the right side, we see that that anion, HCO3, 1 negative, only has 1, implying therefore that H2CO3 has lost one of its hydrogens in order to form products. Therefore, the species H2CO3 is then donating its proton to the water molecules, making that the acid. And not surprisingly, that species H2CO3 is known as carbonic acid. The water in this instance is accepting that proton, meaning water here is acting as our Bronsted-Lowry base. We can use the same logic going in the reverse direction now. For the reverse direction reaction to occur, the species here which contains the carbon must pick up an extra hydrogen to then form H2CO3, implying therefore the species HCO3 negative is our proton acceptor, that is our base, and the hydronium ion here is acting as the proton donor, that is our conjugate acid. So we've got water the base, carbonic acid the acid, hydronium ion the conjugate acid, and the bicarbonate ion HCO3 negative is here our conjugate base. We can apply that same logic for our second reaction here, in which we have the the hydrogen phosphate ion HPO4 negative reacting to the bisulfate ion HSO4 negative, forming the dihydrogen phosphate ion H2PO4 negative and sulfate ions SO4 negative. Let's go through the same logical process we did before to identify the donor and the acceptor of the proton. So in our forward direction, the species which has the phosphorus in it, HPO4 negative, only has one hydrogen attached to it, whereas on the product side, the product H2PO4 negative has two hydrogens, implying in the forward direction, the phosphorus-containing species here has picked up an additional hydrogen, meaning therefore this is our proton acceptor, the base. And by that same logic, the species HSO4 negative is donating its proton to go in the forward direction, implying that is acting here as the Bronsted-Lowry acid. Now for the reverse direction reaction, if we look at that species SO4 negative, this one does not even have a proton to donate, implying the only thing that species could do is to pick up a hydrogen. Therefore, the sulfate ion SO4 negative is acting as our proton acceptor, that is the conjugate base, and the ion H2PO4 negative, that is the dihydrogen phosphate ion, is acting as our proton donor. Therefore, this is our conjugate acid. So just as a brief review there, we now see we can easily identify here conjugate acid-base pairings by tracing the path of the hydrogen as the reaction occurs both in the forward and reverse direction reactions. All right, continuing along here with our discussion of a couple more conceptual questions relating to acids and bases. Example number 4 here is going to ask us to identify the stronger acid species between two chemicals here. Those are hydrocyanuric acid, HCN, or hypochlorous acid, HClO. Now, as it turns out in this particular problem, this is a problem that I cannot immediately answer because neither of those acids is among the list of strong acids we suggested you memorize at the start of our lecture right here. So those two species then, HCN and HClO, would therefore both be weak acids. And in order to determine the relative strength of a weak acid quantitatively, we need some numeric data to support our arguments here. Really what this comes down to is we need to know the values of the equilibrium constants Ka for each of these species. Now there is no way to determine those values of Ka without either, number one, experimentally determining them, or number two, having some sort of data table provided to you. Generally on the AP test, they will give you the appropriate data for you to use to answer this type of question. But for our purposes here, we're just going to go ahead and look up this data here out of our textbooks. If you're using the Zoomed-All book here, we can have a look at table 14.2, which is on page 628, to find the values of Ka for each of those acid species. So as I look those values up here, again, if you don't have access to that book, you're also welcome to look these up on the internet. The value of the acid dissociation constant Ka for hydrocyanic acid, HCN, I find that value to be 6.2 times 10 to the negative 10th. And for hypochlorous acid, HClO, I find a value of the acid dissociation constant Ka to be 3.5 times 10 to the negative 8th. Now recall from our discussions of equilibrium, the larger the value of K, the more heavily the system favors the formation of products. And for an acid, that implies the higher the degree of dissociation of that particular acid, the larger the value of K, and therefore the stronger the acid. So I can identify then that hypochlorous acid, HClO, will be the stronger acid of this pairing as it has a larger value of Ka than does hydrocyanic acid, HCN. Now that's going to kind of directly lead me into an understanding of example number 5 here. In this one, we're looking to find which species is acting as the stronger base, that is the cyanide ion Cn negative, or the hypochlorite ion ClO 1 negative. Now, looking at those two species here, I can see that each of those species is formed from the dissociation of their respective acids from the previous problem. That is, I could write dissociation equations for these acids. HCN separates apart into the hydrogen ion H positive and the cyanide ion CN1 negative, or hypochlorous acid, HClO, dissociates into the hydrogen ion H positive and the hypochlorite ion ClO1 negative. So if I understand the relationships between these species, I can then easily answer this question. Those ions, CN1 negative and ClO1 negative, are acting as the proton acceptors in the reverse direction reaction for the dissociation equations we just wrote, implying, therefore, those species are the conjugate bases in their respective systems. And as we discussed on our previous slide here, we had an understanding that if an acid is a stronger acid, that would imply that it has a relatively weaker conjugate base. And so to answer this question here, all I have to then understand is the relative strength of the acids. As we just saw, the acid HClO, hypochlorous acid, was a stronger acid than hydrocyanic acid, and that would imply, therefore, the conjugate base of hypochlorous acid, that is the hypochlorite ion, would therefore be a relatively weaker conjugate base than the conjugate base of hydrocyanic acid, that is the cyanide ion CN1 negative. So again, the stronger the acid, the weaker its respective conjugate base. And therefore, the hypochlorite ion is a weaker conjugate base. The cyanide ion is a stronger conjugate base. All right, moving along here, having a look at a couple of more reactions here involving acids and bases. I've got an example up on the board here for you in which we are looking at, again, identifying the acid-base conjugate pairs within a couple of reactions. The first of which is water reacting to HCl to form H3O positive and Cl1 negative. This is a relatively straightforward one here. We can identify in the forward direction, not surprisingly, hydrochloric acid is acting as our proton donor, and the water molecule in the forward reaction here is therefore the proton acceptor. So we've got HCl, the acid, water, the base, and then for reverse reaction, the hydronium ion is donating its proton, the chloride ion is accepting, so hydronium is the conjugate acid, and chloride is the conjugate base. Likewise, for the second reaction, now we have water and ammonia reacting to form hydroxide ions and ammonium ions. In the forward reaction, our ammonia seems to be picking up an extra hydrogen, implying, therefore, ammonia is acting as our Bronsted-Lowry base. Water in this reaction is acting as, therefore, the acid. And for our reverse reaction, the ammonium ion NH4 positive seems to be donating our proton, the hydroxide seems to be receiving, and therefore hydroxide is our conjugate base, ammonium is the conjugate acid. Now, importantly here, folks, I'd like you to have a look at one particular species from each of these reactions, that is the water. In our first reaction, water was acting as our proton acceptor, that is the base. In the second reaction, water is acting as the proton donor, that is our acid. And as such, water appears to be a species which exhibits both acidic and basic characteristics depending upon the context, that is, depending upon what it's reacting to. We call those types of species that can either act as acids or bases amphoteric species. Ampho being a prefix which you've seen other places before, places like amphibian, which is something that is equally able to live in the land or water. So amphoteric would imply, therefore, something which is equally able to act as a acid or a base. And importantly, you'll see a lot of different amphoteric substances over the course of our year here. Oftentimes you'll see them as part of the dissociation sequences of polyprotic acids. So for example, if we have a look at the dissociation sequence for carbonic acid, that is the species H2CO3, we will see carbonic acid will dissociate here to form a hydrogen ion, H positive, as well as the bicarbonate ion, HCO3 1 negative. And that bicarbonate ion can further go about to dissociate and form another hydrogen ion and the carbonate ion, CO3 2 negative. So if we have a look at the intermediate ion from this dissociation sequence, that is the bicarbonate ion, HCO3 1 negative, We can recognize that in the forward direction, this species is donating its proton, implying therefore it's acting in that direction as the acid. Whereas if we run these reactions in the reverse direction, that species HCO3 negative is picking up a proton to form the molecular acid H2CO3. So therefore that intermediate ion HCO3 negative can act both as an acid or a base, implying therefore it is an amphoteric species. Now, the most important amphoteric behavior we are going to observe in the course of our year here is the behavior of water. And we'll see why on our next slide this becomes such an important idea to consider. So having seen now on our previous slide that water is an amphoteric species, let's consider for a moment here about what would happen if we reacted two water molecules to one another. Now, that might seem like a kind of weird idea, but if we recognize that water again can act both as an acid and as a base, that would imply that one water molecule could therefore donate a proton to another. And if we wrote a reaction describing that process, then we would see water and water as our two reactants, and donating that proton would then form as products the hydronium ion H3O positive and the hydroxide ion OH1 negative as part of that aqueous solution. Now, this process does occur, however, it is a weak process and therefore is governed by a K value with a very, very small value of K. I've written this reaction again in two different ways. First off is as the hydrolysis process that we just described. We also could recognize that we could write that essentially as a dissociation by remembering that that hydronium ion H3O positive is really just a water molecule associated with a hydrogen ion. And so if I look at it from that perspective, I really have a water molecule on both sides of that equation, which I could cancel out, which would then yield a dissociation reaction, which would be essentially what's happening here is that water is dissociating into a hydrogen ion and a hydroxide ion. The K value for that process would therefore be defined as, again, the ratio of concentrations of products over reactants, which if I write that as the hydrolysis would be the concentration of hydronium ion times the concentration of hydroxide ion, all divided by 1 because remember on the left side of our equation, those water molecules are liquid phase species, therefore at relatively constant concentration and will not really affect the equilibrium position of our system. So we've got a value here of K, and this is such an important value of K that it gets its own unique designation. We call this value Kw, that is the autoionization constant for water. Now, I can experimentally determine the concentrations of those hydronium and hydroxide ions in solution. And if you run an experiment and you find the equilibrium concentration of each of those ions in solution at 25 degrees Celsius, as it turns out, they turn out to be a value of right around 1.0 times 10 to the negative 7th moles per liter of each of those species. That is very, very low concentrations. And with those measured values of hydronium and hydroxide concentration, I could then calculate the value of the autoionization constant Kw in my solution. Kw would be equal to the concentration of hydronium times hydroxide, each of which, again, are 1 times 10 to the negative 7th molar. So I've got a Kw value of 1 times 10 to the negative 7th molar squared, which would give me an autoionization constant value of 1.0 times 10 to the negative 14th. Again, a very small value of K, implying this system heavily favors the reactant side. So the degree to which this ionization occurs is not a particularly strong dissociation. That being said, what that value of Kw tells me then is that I could determine the relative concentrations of hydronium ion and hydroxide ion in order to determine the acidic or basic nature of a solution. Because remember, pure water, again, is only producing those ions via autoionization, implying the concentrations of hydronium and hydroxide must therefore be equal to one another in solution. And as such, we would say a neutral solution of pure water would therefore have equal concentrations of those two ions, hydronium and hydroxide. Let's compare that then to an acidic solution in which we dissolve some sort of acid in water. So if we throw hydrochloric acid in water, again, as we have seen, the hydrochloric acid will donate protons to the water molecules, forming an excess of hydronium ions in solution. And because our autoionization constant tells us that there must be an inverse proportional relationship between the concentration of hydronium and hydroxide, since the product of those two concentrations multiplied together must equal a constant value, If the hydronium ion concentration goes up in an acidic solution, the hydroxide ion concentration must therefore go down by the same proportional amount. So therefore, acidic solutions will contain a higher concentration of hydronium than of hydroxide. Or conversely, again, if I dissolve a base into a solution, let's say, for example, I dissolve sodium hydroxide NaOH into solution, the dissociation of the sodium hydroxide will form an excess of hydroxide ions, which by that same logic would then cause the hydronium ion concentration to go down as well, due to that, again, inverse proportional relationship. So acidic solutions have higher concentration of hydronium than hydroxide. Basic solutions have higher concentration of hydroxide than hydronium. Now, as a kind of hint to looking forward here, if you have a look at some of these numbers that we are seeing in terms of the autoionization process, some of these numbers might start to stick out to you in terms of an idea that you've probably been exposed to in previous science classes. That is, when dealing with acidic and basic species, those numbers of 10 to the negative 7th and 10 to the negative 14th seem in some way related to the pH scale, that is a scale which measures the acidity of a solution, where neutral on the pH scale is a value of 7, and we remember again that that pH scale generally goes between values of around 0 to 14. We'll see where we derive that numbers from in a couple more lessons here, but for the time being, just recognize kind of a little foreshadowing there, that the pH scale is related to the concentrations of these ions in solution. All right, so we now find ourselves at the last slide of our lecture here. We are looking on this slide here to find how we can use data from a provided data table in order to determine if the process of autoionization of water itself is an exothermic or an endothermic process, and we would like to justify our reasoning to explain how we know that to be true. So looking at the data we've been provided with here, we see here at the temperature of 25 degrees Celsius, as we just discussed on the previous slide, the value of that autoionization constant is 1.0 times 10 to the negative 14th. But then recognize that the value of an equilibrium constant is only constant at a particular temperature. We see here if we increase the temperature of the system to 60 degrees Celsius, the value of that autoionization constant becomes 1.0 times 10 to the negative 13th. That is a larger value of Kw, implying at higher temperatures, we see the autoionization process apparently is a more favorable event to occur. Now, in order to understand why that might occur based upon the exothermic or endothermic nature of the process, let's go ahead and look again at the reaction describing the autoionization of water. That is, H2O plus H2O forms the hydronium ion H3O positive plus the hydroxide ion OH negative. And we've seen this sort of technique before in dealing with this type of system, that one of the easiest approaches to do is to simply start with the assumption that the process is either going to be exothermic or endothermic. So knowing that, let's go ahead then and just make an assumption that it's in fact, in this case, going to be an exothermic process. So to notate this as exothermic, I'm going to go ahead and place energy on the right side of my reaction. And let's see if that prediction then fits the data which we've been provided with in our data table. As we recall from our discussions of Le Chatelier's principle here, if we see an increase in temperature, that increase in temperature is supplying more energy into the system, which then could be used to drive the endothermic direction reaction, as an endothermic process is a process which consumes energy. So increasing the temperature of a system should therefore cause the reverse reaction of this process to occur faster, and as such, we would see a shift towards the reactants in our system, implying were this process exothermic, the increase in temperature should cause a decrease in concentration of the dissociated ions H3O positive and OH negative. That decrease in concentrations would then yield a smaller value of Kw at higher temperatures. And looking at our data table, that seems not to be the case we're observing. So it seems like our first prediction of an exothermic dissociation or autoionization seems like the incorrect prediction. So if we've now eliminated the possibility that autoionization is an exothermic process, the only other option, therefore, is the process must therefore be endothermic. So let's go ahead and shift our energy over onto the left side of our reaction here. This is now written as an endothermic process in the forward direction. And applying the same logic, if we see an increase in temperature, the increase in temperature should drive the reaction in the endothermic direction, as that endothermic process requires energy in order to run. And as such, this would cause a shift in our equilibrium position to the right by Le Chatelier's principle. And in doing so, we would see an increase in concentration of our product ions, H3O positive and OH negative. Those increasing concentrations would then in turn cause an increase in the value of the autoionization constant Kw, and therefore we can now definitively say that it appears from the data table that the autoionization process itself must therefore be an endothermic process. All right, so that concludes our introductory lecture onto acids and bases. The remaining lectures within chapter 14 here are going to deal with associated concepts of acid-base chemistry before we move on to aqueous solution equilibria in chapter 15. Thanks for watching.